Hello everyone, welcome back to the course Materials in Sports. In this lecture we will discuss materials for equipment intended for injury prevention in sports, such as helmets and pads. Let's start with helmets, as we know head injuries can be particularly traumatic. Brain injuries are critical in sports, with the highest risk occurring in high speed and contact disciplines. To reduce these dangers, which can lead to fatal events, helmets play a central role in athlete protection. Despite variations across different sports, most helmets share a common structural design consisting of a thin, rigid outer shell and a thicker, more compliant inner liner. The outer shell helps spread impact forces over a wider surface area, reducing localized pressure points and shielding the head from sharp or penetrating objects. It also contributes to durability and overall appearance. Common shell materials include polymers such as acrylonitrile butadiene styrene, ABS, and polycarbonate, PC, while advanced application may use fiberglass, carbon fibers, or Kevlar composites, which have been discussed in Lesson 2. The inner liner functions as the main energy absorber, reducing the acceleration experienced by the head during the impact. This layer is usually made of foams like expanded polystyrene, APS, expanded polypropylene, EPP, and expanded polyurethane, PU. These foams are lightweight and straightforward to process. They can absorb energy through permanent deformation in single impact helmets that must be replaced after a single high energy impact, or through viscous dissipation in multi-impact helmets. This behavior helps keep impact forces below levels that can cause serious injuries, while allowing controlled deformation to enhance safety. To understand how foams works, we must rely on compressive strength versus strain relationship of cellular material made of cells with air inside, such as foams, shown in the figure. The curve can be divided into three sections: the linear deformation part at the beginning, the plateau region, where elastic and plastic buckling of the cell walls occur, and the densification region, which is the steeper part of the curve, where cell walls contact each other and the constituent material is compressed. Energy absorption efficiency is highest in the plateau region. In fact, energy absorbed in the impact is represented by the area under the stress-strain curve, which is maximized by a wide plateau region. An ideal foam absorbs the induced energy in the plateau region without densifying. This area can be tailored by modifying the constituent material, so choosing a different foam, the foam relative density, the same foam can be manufactured in different densities, or the foam thickness. Designers have limits for the thickness, as overly large helmets are uncomfortable, and in addition they can increase rotational acceleration by increasing torque applied to the head, which generates vicious rotational deformation of the soft brain tissue. As such, helmet liner thickness is generally limited. So, combining layers of foam of various relative density and hence stiffness may broaden the range of manageable impacts. Progress in helmet safety is being driven by the integration of biomimetic design principle, high-performance polymers, and additive manufacturing. This combination is transforming helmet technology, enabling the development of liners that are not only safer, but also lighter, more ventilated, and capable of multiple functions, surpassing the limitation of conventional foam-based solutions. In a recent article published in Advanced Intelligence Systems, a new helmet has been designed and 3D printed based on the structure of diatoms, which are unicellular algae. The diatom has a multi-layer structure, an outer porous filter layer, a non-honeycombed middle layer for strength, and an inner layer with reinforced openings. Despite being made of brittle silica, its hierarchical design gives strength, toughness, and multifunctionality. This sketch represents the diatom-inspired helmet concept, a combination of biomimetic architecture and hyperelastic polymer, a thermoplastic polyurethane, TPU, work together to generate a new concept capable of supporting multiple functions. If you want to know more about biomimetics in sport, this topic will be covered in the next lecture, in Lesson 5. To generalize the previous example of the diatom-inspired helmet, we can mention the use of metamaterials in safety protection. But what are metamaterials? A metamaterial is a material that gets its unusual properties mainly from engineering internal structure, not just from its chemical composition. Metamaterials are built from careful design repeating unit cell, often at the micro or nanoscale, that give rise to properties not normally found in conventional materials. The advent of 3D printing technologies, both for plastics and metals, has enabled the manufacturing of lattices, auxetic, and honeycomb structures which can tailor stiffness, strength, and energy absorption. I have added the website of the UK Metamaterials Network into the supporting materials for this lecture, where you can find more information about metamaterials research and applications. Another interesting class of materials for sports injury prevention is shear thickening fluids. To understand how these materials function, it's useful to look at the different rheological behaviors of fluid, that is, how fluid deform when they are subjected to shear stress. Newtonian fluids are the simplest case. Their deformation is directly proportional to the applied shear stress, meaning their viscosity remains constant. This appears as a straight line in the graph. Many fluids, however, do not follow this Newtonian behavior. For example, viscoplastic fluid act as solids until the applied shear exceeds a certain threshold, after which they begin to flow. Shear thinning fluids become easier to deform as shear stress increases. In other words, their viscosity decreases at higher stresses, so less force is required to maintain deformation in the high stress region. Shear thickening fluid, by contrast, respond in the opposite way. Their viscosity increases as shear stress rises. This makes them harder to deform under high stress, an effect that can be exploited for impact protection. The mechanism of shear thickening fluids is based on suspended particles in the fluid that lock together when a high energy impact occurs, increasing viscosity. This reversible transition makes them flowable under normal condition, but rigid under sudden impact. Shear thickening suspension usually consists of a dispersed phase, mainly inorganic or organic particles such as silica, titania, calcium, carbonate, cornstarch, or polymer nanoparticles, and a viscous carrier fluid, mainly polyethylene glycol or ethylene glycol. Shear thickening gels are also available. Unlike suspensions, these are homogeneous polymeric systems exhibiting shear thickening properties because of their cross-linked networks. Compared to the shear thickening suspension, the gel networks are more viscous and stable in terms of less sedimentation of the dispersed phase. Over the past few years, several companies have developed a wide range of shear thickening-based products having different peculiarities. Shear thickening materials have been introduced in elbow, knee pads, back, or chest protectors. Shear thickening fluid pads have been proposed in helmets to reduce rotational deformation, as discussed in this patent. In the supplementing material, I added some videos showing how shear thickening materials have been implemented in devices for impact protection. Before heading towards the end of this lecture, I would like to highlight that the journey towards athlete safety is never ending. A good example is Formula One, where continuous improvement of equipment and procedures reduce remarkably the number of fatalities among pilots. I would like to mention the accident that occurred to Felipe Massa in 2009. A big spring, around 800 grams of mass, detached from a preceding car at high speed. The spring struck Felipe Massa helmet just above the visor at about 260 km per hour. Massa was knocked unconscious and crashed straight into the barrier at full speed. He sustained a skull fracture and concussion, requiring emergency surgery, but eventually made a full recovery. Massa's accident highlighted a vulnerability at the upper edge of the visor opening, where the helmet structure was weaker. As a result, the International Automobile Federation, which regulates all equipment used in Formula One, required the manufacturers to introduce a new safety feature called the Xylon strip, officially the Xylon visor panel. A plastic strip reinforced by Xylon, a high-performance fiber, also used in ballistic armors, was placed across the top edge of the visor opening, bonded directly into the helmet shell. Designed to resist impacts from flying debris up to 225 km per hour, Xylon was chosen because it offers extreme tensile strength and impact resistance, outperforming another high-performance fiber, Kevlar. We have come to the end of this lesson, so let's quickly recap the key points. We looked at the materials currently used to keep athletes safe, typically combinations of hard shells with foam padding. Then we explored some of the exciting innovations on the horizon, like metamaterials, shear thickening fluids, and of course the well-established world of fiber-reinforced composites. I hope you enjoyed this session, and I look forward to seeing you again soon for another lesson in Materials for Sports.